Remember that some probabilities are easier to compute by finding a complementary probability. A similar situation holds for conditional expectations. Suppose we want to find the expected value of x given some event A. So the expected value of x given A is going to be the sum of the payoff times the probability of x given A. But if we multiply by the probability of A itself, then this probability of x given A times the probability of A, well, that's just the probability of x and A. And similarly, the expected value of x given the complement of A, again, that's the payoff times the probability. If we multiply by the probability of the complement, we get, and again, that gives us the probability of x and the complement of A. Consequently, if we add the two probabilities together, the payoff can be factored out, and this sum is the probability of x itself, which gives us the expected value of x. So let's consider the following problem. Suppose you roll 5 six-sided dice, find the expected number of sixes, given that there is at least one 1. We'll let x be the number of sixes and y be the number of ones. We want to find the expected value of x, given that y is greater than or equal to 1. So we can compute all of the conditional probabilities. So first we find the probability that y is greater than or equal to 1. Well, that's the complement to y equal to 1, and so that probability will be. To find the probability that x is equal to 1 and also y is greater than or equal to 1, we note that if we put this together with the complementary probability where y is equal to 1, what we get is just the probability x is equal to 1. And so that says that the conjunction will be, and we can compute that, and so our conditional probability is. Likewise, the probability that x is equal to 2 and y is greater than or equal to 1, together with the complement, gives us the probability that x equals 2. And so we find and similarly for x equals 3, and 4, and 5. And consequently, we can find the expected value. Now, that's quite a bit of work. So remember, one way of learning math is to solve the same problem in several different ways. So let's solve it again. So instead, let's go ahead and use this relationship we have between the expected value of x and the conditional expectations. And again, we can think about this as the conditional expectations times the probability that they will be relevant. Since x is the number of sixes we get when we roll n equals 5 dice, it's binomial with n equals 5 and p equals 1/6. So our expected value of x is, we've already determined the probability y equals 0. And if y equals 0, then the die could only land at 2, 3, 4, 5, or 6. And so we can treat this expected value of x, given that y equals 0, as the expected value of a binomial probability, where n equals 5, the probability of success is 1/5, and so our expected value is. Finally, we know the probability that y is greater than or equal to 1 will be. And now we can solve for the expected value of x, given that y is greater than or equal to 1, which will be. And it's the same number we got before, which is a good sign. But let's solve it again. Let's introduce an indicator variable, in, where in is 1 if the nth die shows a 6 and 0 otherwise. So we want to find the expected value of the sum, given that y is greater than or equal to 1. So let's start by finding the expected value of I1, given that y is greater than or equal to 1. We need the probability the first die is a 6, given that there is at least one 1 among the dice. And so that means we need the probability of the conjunction. And remember, the complement is often easier to work with. This y greater than or equal to 1, that's complementary to y equals 0. And here's the important thing to remember. These are actually independent events. The probability the first die is a 6 is independent over the probability that the other dice don't include any 1s. And so we can find this probability by multiplication. The probability that I1 equals 1 is 1/6. The probability that there are no 1s in the remaining dice is, and the complementary probability will be, and so this probability is. And so our conditional probability is, since the INs all have the same distribution, then all of these conditional probabilities are equal. And by the linearity of the expected value of a sum is the sum of the expected values. And we get our third answer, which agrees with the other two.